Thank you very much, Professor Shubham, for the introduction, and thanks for having me here. Uh, Welcome you all, and good afternoon. As you already know who I am, so I'm not going to waste any time on that. Um, so I have been talking about cryogenic CMOS, uh, modeling, characterization, quantum computing, these kind of things, uh, at the most in last 2 years. Before that, I was talking about largely reliability. I still do talk about reliability. And before that, I was talking about CMOS scaling. So you see which direction is the academic research is going, because in academics you have to stay far ahead of industry, but at the same time close enough so that you can get some dollars for your work, right? Um, Today we'll talk about cryogenic CMOS modeling. As I said, this is a fairly new area of research, at least in India. Um, 20 years ago, there was probably 4 to 5 large groups globally who used to work in cryogenic CMOS. One of the groups was at EPFL, where Professor Yogesh Chauhan went for his PhD. I also had a bit of interaction with that group. My voice is audible? Yeah. So, those people, group of Professor Christian Ange, they have been working using cryogenic measurements for a very long time. Couple of groups in the US, also primarily related to military applications, have been looking at cryogenic CMOS early on. And then there are few very renowned groups, I'd say, who had very large cryogenic setups. One place is IEEE Mexico. They had cryogenic setup from very long time ago. Professor Edmundo Gutierrez is the director of that center right now, and they have written very nice books. Corclais and Edmundo have written a very nice book on cryogenic CMOS 10 years or even longer ago. But to us, this is relatively new, and this idea really picked pace ever since quantum computing sort of became more visible and more talked about thing. We are having this distinguished lecture under the aegis of IEEE Electron Device Society. Majority of you already know about EDS. Some of the EDS veterans are here. For those who don't, EDS promotes all kind of electron devices related research, and it's a very well established and well known society within IEEE. It's not one of the largest, but it's one of the I'd say oldest, right? And so people who are in EDS have been very well known to the entire IEEE spectrum, and EDS has lots of good journals where our kind of work gets published. Transaction on Electron Devices, Electron Device Letters, Journal of Electron Device Society. All these are very good journals. I am currently associate editor of Transaction on Device and Materials Reliability, which is also falling under EDS. So as I said, EDS field of interest is all aspects of device physics, simulation of electron devices, various kind of metals, organic materials. So EDS is very vast in that sense. It covers very broad spectrum of different kind of materials and devices. And there is, of course, EDS membership comes with lots of benefits, especially to the students at a very subsidized cost. So those of you who have not joined EDS and are considering, please do join EDS, and you get a range of advantages by becoming a EDS student member, and that's where your EDS journey starts. And as you progress further in research, EDS is going to stay with you and lead you to newer horizons all the time. With that, my message is, please join EDS if you have not already done so. Here is the outline of my talk. So I'll try to briefly motivate you about why we want quantum computers. I'll not go too much into detail of why we want quantum computers, because I assume everybody who is in this room has already is well read, at least. If not the journals, you read the news items, and so it is everywhere, right? So I'd rather go a little bit specific and talk about why co-integration of CMOS with qubits could be interesting. And then we'll talk about cryogenic CMOS operation and compact modeling. I'll briefly talk about the measurement setup, some of the key results we obtained so far, and then I'll try to summarize. So quantum computers, there's a lot of talk about quantum supremacy. What we are saying is that, give me a couple of minutes to explain why quantum computers are important. So quantum computers is not just one word, it actually is multiple things, which is all falling under quantum computing sort of paradigm right now. People are talking about quantum computations, people are talking about quantum communications, and various other things related to quantum computers. So when we talk about quantum computers here, our eye is really on the general purpose kind of a quantum computer, which can do general purpose computing. There are lots of versions and variants of these that many industries have put in a lot of money already behind. Starting with, there is IBM Q, right? IBM Q is a quantum computer that IBM has made available to entire academic community worldwide. You can run your quantum algorithm on IBM Q using the IBM cloud, right? So it works more or less like how Purdue Nano Hub works. You submit your job and at a particular time it gets executed, right? So IBM Q is there. Then of course Google has very large investment in quantum computers. There is D-Wave, and then there is lots of academic groups working on this. IBM, for instance, is focusing primarily on superconducting material based qubits. Okay, in a moment we'll talk about what qubits are. While some other companies, for instance, Intel has a collaboration with institute in Netherlands, Kavli Institute. So they have a QTech program and they are focusing on semiconducting qubits. So different people are using different kinds of qubits. They are making quantum computers. There are also lots of companies which are making things like quantum simulators. So quantum simulator is sort of again a simulation tool. It tells you upfront that if you have a certain algorithm, if you had access to a quantum computer, how would that perform? It is still going to run on a classical computer, which is the computer we are familiar with. Then you have the category of quantum annealers, right, which fall somewhere in between the two. So there is new kinds of scaling happening. People are trying to increase the number of qubits. There is new kinds of laws being proposed, just contemporary with Moore's law, right? So these guys have their own law, Rose's law, and so on. There are many new laws coming up. So a lot of activity is happening on quantum computer, and if you pick up any journal like high-level journal like a Nature Electronics and so on, you will see it is full of research in this area. So qubits, let's just talk about the supremacy. So supremacy is basically saying that a computational problem that a classical computer will take forever to solve can be solved using a quantum computer within a matter of few minutes. Okay. Now these problems are very, very diverse. You can talk about stochastic calculus for tracking the stock market. You could talk about ab initio simulations of new materials, molecular synthesis used for pharmaceutical usage. You could talk about cracking a RSA type code, right, which is required for a lot of your security, including the bank accounts and so on. So all those are different areas where quantum computers can be useful. So it has usages right from health sector onward to banking, onward to national defense, even where you are talking about cryptos and so on. Now the qubits are, so we are familiar with logical bits. A bit holds a 0 or a 1, right? It is a bistable circuit. So it can hold either a 0 or a 1, nothing in between. When we are talking about quantum bits, we are saying that you have 0 and 1 and the superposition state of that 0 and 1. So it can in fact take infinite available and possible states. So it can be under superposition, it can be anywhere between a 0 and 1 and sort of linear combination of those two states. Okay, so that's where a bit of quantum mechanics gets involved. It's a very, very interesting research area for students with physics background, with quantum physics background. So then this entire new segment of knowledge that is created and is now being called quantum information theory, right? So quantum information theory tells you how quantum systems work and how to work with those systems. What are the quantum gates, right? What are the different kind of states that you can initialize a qubit into and then you can read. Lot of this, as I'm saying, it's extremely fragile, requires cryogenic operation, because if you remember the famous Schrodinger's cat experiment, right? If you try to see whether the cat is dead or alive, cat dies, right? So the idea behind this is very important, that your observation, you are trying to measure state of a quantum system, that observation itself destroys or at least affects the state, right? So now how do you measure the state? And if you don't measure the state, you can't do any useful work. So then you try to entangle qubits. You take, let's say, 2 qubits and make one qubit completely dependent on the other. So you initialize the first qubit onto some state, perform some quantum operation on that qubit. The entangled qubit is only going to follow this paired qubit, and you can try to observe the entangled qubit, right? From that you can measure what quantum state it is in. Of course, this is a process where entanglement is related to a lot of crazy new things like decoherence time of qubits and so on, details. So any noise, any thermal vibration can corrupt the state of this system and can destroy the entanglement. So it has to be isolated from the surroundings as much as possible. So we try to reduce all kind of noise, and we even try to reduce the thermal noise. So we cool this entire thing. We have to cool this entire thing down to millikelvin temperature. Okay, a millikelvin temperature, I'll show you, is actually colder than the coldest place in the universe. So absolute zero doesn't exist. Physicists can give a counter argument, but practically absolute zero doesn't exist, and millikelvin is the coldest that is there anywhere in the universe, which is in our lab, right? So that's a big achievement. So of course a new range of equipment is required to do this kind of work. Qubits, like as I said, there are superconductor based qubits, there are semiconductor based qubits, depending upon what your qubit is. Qubit can be charge based, it can be spin based. So you need different kinds of circuitry to read and write onto and from the qubits, right? And all the time you are of course always worried about any noise that is introduced in the system. I'll also cover that briefly. So cryo CMOS, the idea is you anyway require a classical computer to operate a quantum processing unit. So a QPU cannot live without a CPU, because CPU is the one which is talking to the external world and doing all the heavy lifting work. It's only a critical part of your algorithm. Think about it like a critical logic design path where you put more emphasis during logic design. So only a critical operation you pass it on to the quantum processing unit, and it does that. And even after it does that, this is a statistical process. So you are always talking about expectation values. In quantum mechanics, there is no absolute value, right? So you are doing multiple same operation. You are replicating on hundreds and thousands of qubits, and then you are looking at the statistical averages of what happened as a result of that operation, right? So of course, when you are talking about hundreds of thousands of qubits, there is going to be interconnection, right? You have to connect the qubits so that they can talk to each other, they can talk to every other qubit depending upon how complex your system is. So there's going to be a lot of interesting work that will come out on the interconnection side, and all the systems packaging discussions that we are having in various forums, that is also going to come very handy. So now when we talk about anything which is 100,000, million, billions, your attention immediately goes to CMOS, right? This is the only technology where we have successfully manufactured things in billions and controlled them and reproduced them, and these are production level things. So doing this kind of work, if you are doing with 50, 100 qubits, that's fine. But if you are really talking about a general purpose computer which can solve real large quantum algorithms, you really need very, very large number of qubits. And added to that, the issues that will arise out of various kind of noise and disturbances that your qubits will see, you have to build redundancy in your system, right? This is what they call about the error rate, right? So you have to do a lot of error correction. So in order to get the correct statistical average of your outcome, you are replicating the same operation on 100,000 qubits. So one logical qubit is 100,000 physical qubits. So if I have 100 logical qubits, I am already talking about 10 million physical qubits, right? Just for 100 logical qubits. So that's the kind of scale of things. Of course, the more you can draw from this reduced noise and so on, you can reduce your redundancy in the system. But NISQ is noisy intermediate scale quantum system. That word will come from where? At this moment. Sorry? Oh, okay. All right. So if you try to sort of reduce noise and so on, you can reduce redundancy going forward. Currently, we are talking about 50 to 100 qubit logical qubits, which is, depending upon your error in your system, can very well mean from 100,000 to a million qubits. And when it comes to interconnecting million qubits, by default everybody will look up to the CMOS kind of industry. Okay. So we move forward. So what is cryogenic temperature? I have just taken some things off the internet, may not be very accurate. So Earth's surface, so minimum temperature, all temperatures are in Kelvin, right? This is the temperature on the moon. This is minimum and maximum. And outer space is kind of the lowest, 2.7 K. And liquid helium, very important, is what is used for most of the cryogenic probers. 4.2 Kelvin, liquid nitrogen is at 77 Kelvin. We are talking about cooling our qubits down to 10 millikelvin. So that's why I said it's the coldest in the universe you can go, right? I don't know, maybe inside black holes it could be lower than that, but nobody is going to be able to go there and measure. Of course, remotely you can try to do that. So what's the current scenario in this area? This is the current experimental scenario in this area. This is what is called as a dilution refrigerator or dilution fridge. Primarily two companies manufacture it. One is called Blue Force, another one is Oxford Instruments. Okay, these are the only two companies which are manufacturing it. Depending upon the requirement, you can get a bigger diameter of the sample stage to fit in your 300 millimeter wafers and so on. So the cost of the fridge will go up and down. Typically there is an intermixing stage where mixture of helium-3 and 4 basically gives you the 10 millikelvin kind of temperature. Then there is a 4 Kelvin stage roughly, which is at the liquid helium temperature. You can have 70 higher temperature stages as you want. This entire thing is one big cylinder-like structure, right? If you go back to my very first slide, this is a view how from inside a dilution refrigerator looks like. Okay, this is just the inside of the dilution refrigerator. All these wires you see are your lines to connect your devices to the outside world. So coming back here, there is of course a feed through kind of a port. Then you have your instrument rack, arbitrary waveform generators, microwave source, DACs, oscilloscopes, digitizers and whatnot. And now the interesting thing is, if you are talking about, let's say, 100 qubits, you want to measure 100 qubits at the same time. One qubit requires, if you talk about a silicon based spin qubit, one qubit requires roughly 10 connections. Okay, so those 10 connections you connect from outside world. So 100 qubits are going to require 1000 connections, right? How many wires you can run? Then also you have to think about the thermal load. So as your temperature goes down, the thermal load capacity of your system goes down. So they are going to offer you something like 100 microwatt, 50 microwatt of thermal load at 10 millikelvin stage. So if you connect these qubits to too many wires which are coming from room temperature and at higher temperatures, this is never going to cool to 10 millikelvin. So the trouble is, 1 or 2 qubits you can measure this way. But if you really want to measure 100 qubit system, which means roughly million of physical qubits, how do you go from here to here? Let's say you route your lines to this 4K stage. So a lot of people are trying to design chips which are called cryo controllers. Okay, so Intel has a series of cryo controllers which primarily sit here, do multiplexing. So these will connect to, let's say, 100 qubits here, while this may connect to just 10 lines outside. You do that multiplexing 10:100 here, and you also have to take care of the noise. So you have a lot of low noise amplifiers and so on sitting at that cryo controller level. This is one area where Intel is leading. They have now almost third generation of cryo controller launched, right? But they are not selling it. They are doing it for their own work. They are publishing it every year in IEDMs and VLSI symposia, but they are not selling it. It's not available to customers yet. So anybody who wants to do serious work with quantum computer as a system, not just one qubit and showing its states and so on, you are first stuck here, right? I'll just give you an idea. So this dilution refrigerator at the least will cost you in Indian currency 4 crore rupees as of today. This instrumentation, if you do for even a 4 qubit parallel measurements, which have to be phase logged and lot of other things, this is going to cost you another 5 crore. So this is already like 10 crore system to measure 4 qubits at the same time, parallel measurements, right? If you want really to do any algorithm level work and so on, you first have to design your own cryo controller. Okay, so this is a good thing, because whenever we do technology, we want to take designers along, right? So we are also giving our requirement to designers, and people are very interested, because this is all going to be, now you see, this is cryo CMOS. So that cryo controller chip, all those LNAs, multiplexers, you are going to design at 4 Kelvin temperature. So this CMOS has to work at 4 Kelvin. That's where cryo CMOS is important. Then you talk about co-integration, then you are saying not only the cryo controller here, I want to make these qubits also out of CMOS. How? Well, if you look at the quantum effects in a very advanced short channel MOSFET like a nanowire transistor or a FinFET in 7 nanometer node and so on, there is very strong quantum confinement, because your channel is limited in volume. So earlier when people were doing bulk CMOS planar devices, channel volume was fairly high, but now we are doing fin based devices only. We are not doing planar transistors. So it is confined from all the directions, right? So you're talking about a nanowire of, let's say, 3 nanometer diameter. So it is very, very highly confined, and because of that confinement, you again have all the laws of quantum mechanics applying to this, right? So you can talk about particle in a well and so on, and when you try to do that, you see that the transistor itself will show you when an electron enters the channel. You can detect quantum oscillations. So you will see, you can use a advanced short channel MOSFET or FinFET as a single electron transistor. If you are at sufficiently low temperature, how low will depend upon charging energy of your transistor, depending upon the gate capacitance and the excess resistance of the device. So some of my students who are working in this area, they have recently submitted a very nice paper where they have very controlled quantum oscillations in a 10 nanometer FinFET that was made by IBM in their 10 nanometer technology. So it's not a, it's not a impossible thing to use CMOS itself as a qubit. Currently what people are doing, I'll also try to show you, but if you have gone through the papers, people are looking at a lot of heterostructures to make the qubits. They have a lot of accumulation and depletion gates to concentrate the charge in one place, right? And then using a designated single electron transistor which is monolithically integrated, you detect as the charge goes from one quantum well to another, right? That's what people are trying to do. And of course, if you are looking at spin sensitivity and so on, then you need microwave, and you are then looking at the resonant circuits, resonant frequencies you will detect, and you will be able to both initialize electrons in a particular spin state and also detect them. So there are Rabi fringes and a lot of things that are happening. So cryogenic operation, by now we know it's low temperature operation. So now we are interested to know not just because we want to do CMOS control electronics, we also want to make qubits someday in CMOS. So we are really interested to know how CMOS will behave at cryogenic temperatures. Of course, as you would expect, performance is going to be improved, primarily because subthreshold slope is going to be very steep. So transistor will behave much better as a switch, but finer details we don't know, which is where the devil is in the details, right? So unless you compare what kind of length scaling impact is happening in cryogenic regime, what kind of width scaling impact is happening, how NMOS is behaving versus PMOS, all those things, unless you sort out and make a real good compact model, you can't really design a cryo controller, right? So any of the foundry models, whether it's ST, Global Foundries, TSMC, none of them go down to this kind of cryogenic temperatures. They all are typically going to minus 40 C, which is where the standard compact models are. So we need to look at those, and then of course some of the old research topics like self-heating is very important as your devices become small. And now remember, you have only 50 microwatts of heating load capacity, thermal load capacity. So if self-heating starts to happen, you may never be able to actually reach this kind of temperature, right? So self-heating becomes very important again. There are of course reliability concerns. We have never operated transistors at these kind of temperatures, so we don't know how transistors will operate, how the reliability, things like hot carrier. So basically we want to look at everything in the cryogenic regime and make sure that it works the way it was working at room temperature operation. So as I said, subthreshold swing. So of course there is Boltzmann limit. So if you take a conventional transistor at room temperature, this KT over QL in 10, you basically get 60 millivolt per decade as the smallest amount of subthreshold swing you can get. Lot of people who have worked on tunnel FETs, they know you can get lower than that at room temperature. But in cryogenic area, this doesn't work because you are not at this value, right? So the Boltzmann limit will not hold. So SS will deviate from this value below a critical temperature, and based on our measurements we have found what kind of critical temperature we are talking about, and that's where we try to augment the compact models. Reasons, this is, I would call this as the prevalent reason. This is what most people believe is what is causing this, but there may be other things happening. So these are all hypotheses, right? As long as somebody challenges it, everybody goes with this. If a better proposal comes up, then everybody starts looking at that direction. So we are in compact modeling area more measurement and observation based, right? We have looked at, for instance, threshold voltage modification, and there are various competing phenomena, like band gap widening, incomplete ionization, Fermi potential, then interface traps. So all of these are giving different kinds of effects on the threshold voltage, and you really have to see for a particular device which way it is going, which effect is dominating, which is again a function of lots of things, right? But overall, you would see that the threshold voltage will saturate at some point, right? It will not be monotonous increase or decrease. That saturation effect is very important. On mobility, this is the good old mobility curve everybody is familiar with, right? ionized impurity scattering, phonon scattering, surface roughness scattering, all that at room temperature. It holds true down to -40°C, down to even -100°C, it will also hold true. And these are the scattering mechanisms we talk about: electron lattice, defect scattering, this boundary scattering, kind of surface roughness scattering, right? So effective mobility, we have seen that it increases in cryogenic temperature because of the decreased scattering events. You are trying to freeze everything, so things are vibrating less and less, right? The vibrational energy is going to be lowered, right? So scattering events are going to be less. So we have seen that Coulombic and surface roughness scattering dominate at low temperatures. Is clear, right? Since you are controlling the vibrations, phonons are not going to be doing much of a change in the mobility. Self-heating, everyone is familiar with this kind of conventional self-heating concept. So we have a SOI FinFET here, which is sitting on this SOI film is sitting on a buried oxide. So if you generate heat here while the device is in operation, then where can that heat go? It can go laterally, left and right. Depends whether there is a device next to it or not. Usually there is going to be STI, some form of STI next to it. Although SOI you can use MESA for isolation, but you still will have some kind of a filler oxide before the next device. So not much heat will go left and right. It can't go downwards because there is this thick buried oxide, which is a bad thermal conductor. So the only way is actually up through the gate and up through the tungsten plugs in the source drain contact, right? So SOI, as a result, this area will start heating. So your junction temperature is going to be higher than the ambient temperature, and that has been a concern for SOI ever since this was started, that it will suffer from self-heating. If you look at the bulk devices, of course the heat can go downwards, right? So conventionally you would say that this is better off, but now you have only FinFETs. You don't have bulk planar FETs. So if you look at the third dimension of this, right, into the world, your fin is what, 5-6 nanometer wide, right? So that's the only contact of this fin with the actual substrate, which is again going to limit the transport of this heat downward. So now if you look at FinFET, bulk and SOI are equally poor in terms of thermal conduction, and they will give rise to similar kind of increase in the junction temperature. So inadequate heat dissipation will obviously lead to significant local temperature rise, and this can give rise to, you know, changes in carrier mobility, threshold voltage of the device, and so on. So this is actually a very big challenge. Every time we do measurements and publish a paper, we can look at the substrate, the chuck temperature, which is where our thermal sensor is going to be mounted. But a reviewer will always ask, what is this temperature? You are saying I have done measurements at 4 Kelvin. 4 Kelvin is where this wafer is kept. You know there is self-heating. How do you know temperature here, right? So of course you can think about things like using one FET as a heater and one FET as a sensor to do this. You can have gate resistance kind of structures where you can do Kelvin measurements on gate resistance to figure out the mobility in the temperature in the channel underneath. So all those extra things have to be done in order to be sure about if your channel temperature is indeed what you are claiming it to be. So self-heating is a big impediment in this kind of work. As I said, this is a TCAD picture drawn at 300K. This is a TCAD picture drawn at 100 millikelvin. You can see very different distribution of heat between the two pictures. Basically what they are saying is, since the phonons are not going to be scattered much, you are really talking about a concept of phonon black body radiation, where phonons really have a very, very large mean free path and they carry the heat without much scattering, right? Similar to what happens with photons. That's why they call it a black body radiation. So this is the effective mechanism in the absence or almost absence of scattering events at cryogenic temperature. So if you look at the devices, so we are showing you the increase in temperature because of self-heating. Okay. So what you would see is that as you are changing this power in milliwatts, this is of course a simulation result, you would see that self-heating will change. So it will go to different amount of self-heating. So the red color, if you red and yellow, these colors if you track here, these are at lower at higher temperatures. As the temperature goes lower and lower, your rise in temperature is becoming much higher, right? So at 300K and close to room temperature, the rise is just 10 Kelvin from the ambient temperature. At 4.2K, the rise is already at 6 milliwatts of power. It's already 50 Kelvin. So what it's saying is that temperature rise exceeds when you cool down. So self-heating will become more of a problem, right? Your junction temperature is going to be even more different from the ambient temperature if you are in the self-heating regime in the cryo temperature. So this puts sort of more onus on us to actually measure self-heating, which is not straightforward. Well, a lot of heat is actually getting dissipated because of these phonon scattering events, which are not happening at these kind of temperatures. Mm-hmm. Well, that's what I'm saying. So we don't know for sure. Okay, it really depends upon what TCAD models have been used inside this simulation to come at this. But most likely, whenever we do TCAD simulation, we use full thermodynamic model. Okay, so that takes into account actually all kinds of effects that are possible. But thermal conductivity changes in cryo range are also not well documented. So we know, for instance, what happens to, let's say, silicon thermal conductivity between room temperature and -40°C, -50°C. But there aren't really solid measurement evidence as to what happens at 4 Kelvin. So that data is actually not available. We have searched the literature, not just us. This is a paper from someone else. A lot of people have had these issues, and there are multiple theories people are proposing. So we are not sure that what happens at cryogenic temperature, which way the thermal conductivity goes. Okay, so this is active research topic. What we have observed from simulation is that we would call this as a poorer thermal conductivity at lower temperature. That's why your junction temperature rise is more at low temperature, right? So it's equivalent to saying that thermal resistance of my device has increased, right? Which is 1 over the thermal conductivity. So thermal resistance increases, and people have prevalent view is that absence of phonon scattering is what is causing this. Okay. It's possible, but at the material aspects we have not looked, very thoroughly. We mostly focus on the device side of it, but definitely this is an active research area. So since you mentioned, I'll definitely have my students explore that. Okay. Hmm. Yes, that's what we are seeing, right? So thermal resistance increases, that's why the delta T is increasing. So far, as I said, prevalent view is that this is black body radiation kind of a thing. So you are not able to carry all that heat out, right? So a phonon is leaving the channel, right? Leaving the hot area without much scattering events. That's basically what people are saying. Okay. So if we talk about quantum, how much time I have left, Professor Sai? 18 minutes left. Okay. Just let me know when to stop. So quantum confinement effects, I briefly touched upon earlier that you would want to look at the qubits made out of CMOS itself. Of course, qubit fabrication, if you look at the qubits published in IEDM's VLSI by various groups, People are talking about gates which are 3 nanometer, 5 nanometer, right? And not only that, these 5 nanometer gates have a 10 nanometer pitch. So 5 nanometer gate, then 5 nanometer space, next 5 nanometer gate. So we are talking about working with 10 nanometer pitch. Of course, we have 7 nanometer node, 5 nanometer node available. So people are doing it, but how they are doing it? They are doing it with LE approach, right? Litho etch. So you are doing multiple exposures, multiple etch steps to come down to that pitch, right? So that for an industry, for a commercial flow, it is far more optimized and far more suitable to do. But for a research group to do that kind of multiple exposures to reach this kind of pitch is extremely difficult. So majority of them are taking E-beam to their help. Professor Sudha Satta from IIT Bombay is doing this kind of work. He recently showed me his results. So he's trying to make a heterostructure based qubit, silicon, germanium. So he has results using E-beam, and he is able to reach 10 nanometer width of the pattern, but more like a pitch of 30 nanometers, okay, using E-beam. But E-beam, the problem is it's a research tool, right? Whatever you do on E-beam, you can't really ever send it to production because throughput is very, very low. It's a raster scan on entire 300 millimeter wafer, very, very slow, right? So optical lithography wise, it can be reached, but will be very difficult. For industries it is possible. For people like us, it's going to be very tough. So we are currently exploring, as I said, the possibility of using CMOS devices itself as the qubits. IMEC is doing a lot of work in this. They have talked about 2D bilinear arrays and things like that, how to arrange these qubits. But in the noisy intermediate scale quantum, as I said, 50 to 100 qubits right now, this seems to be something that can be implemented. Again, that 100 is multiplied by your error correction rate, right? So how error prone your system is, or otherwise you talk about gate fidelity of quantum gates. So if the fidelity of your quantum gates is very poor, then of course your factor that you multiply to those 100 qubits is going to be far more, many orders of magnitude higher. So implementation of silicon spin qubit in CMOS, this is a schematic people have published. So basically the same CMOS, you have a gate here, you have a gate here. So basically using these gates, you can create islands of charge and use this as a quantum dot. Of course, you can couple your microwave using a bias key with the DC bias, and that's how you can read and write on these qubits. Of course, in a full qubit, you will have a single electron transistor sitting somewhere close by, and you will also have to make magnetic field. So you will have to put some kind of cobalt islands as magnets, nano or micro magnets, to operate the qubit. But the idea is, this is like a proposal from system level people, that you can have a CMOS processor and you can have the drivers and detectors and this quantum processing unit sitting in between. So this part stays at 4K. So this is basically where your complete thing will be. The problem is, if you make these kind of silicon spin qubits, depending upon the charging capacitance, right, the gate capacitance and excess resistance, the qubit can perform down to a certain temperature. So what you can do with those 3-5 nanometer kind of patterns gates, you will have to go to sub Kelvin temperature to operate your qubit. But if you were able to make it, for instance, smaller, then of course you can operate it at a higher temperature, right? So the superconductor based qubits have definite advantage at some of those, but people are trying very hard actually to get this number up and trying to see, can we make a qubit which can operate at 4 Kelvin? So we don't have to go to 10 millikelvin, we can just stay at the liquid helium temperature, right? That will be much easier to work. So those are the things a lot of people are trying to do. So idea is, people are proposing single chip CMOS based quantum computers. And think about, if you have to put some superconducting qubits here, then this whole thing cannot be integrated onto a single chip, and that will create, then you have off chip communication, which will again slow things down, and you have classical problem with you know, the latencies and the bandwidth and so on. So if it all can be on a single chip, nothing like that. If not on a single chip, probably on a single package, that would even be better, right, in terms of integration and so on. So let's see where it goes. As I said, there is strong quantum confinement effect present, so which basically gives you, so you have the barrier gates and gates using which you cause accumulation of carriers, and gates using which you cause depletion of carriers. So that's how you form these quantum dots in the silicon, and typically you have one large source drain at the end, right, which is where your charge is, and you pull that charge using these gates. So they have many gates. That's why to operate one spin qubit you probably require at least one microwave line and 8 to 9 DC lines. You know, all our probers, right, including cryo probers, can accommodate maximum 6 probes, right, 6 to 8 probes. So even a single qubit you can't measure using a prober, right. So then little bit for the compact modeling side. So everybody knows that compact models are very important for doing any design work, right. Of course, BSIM CMG is industry standard. Professor Chauhan is affiliated with that group, right. He has done a lot of work himself on this. So we have tried to put the stock BSIM CMG model next to our cryo measurements. We saw some need for specific model augmentation, which is what we have tried to do. This is a measurement setup that we have. This is a Lakeshore cryogenic prober. Couple of students from IIT Kanpur have visited and performed measurements on this. This is under IIT Delhi Central Research Facility, also part of the Sathi grant from DST. So this is open to everyone, all the students of IIT Delhi, all the students of other institutes, all the industries also, and this is on charge basis. So I have set up this lab, but even my students have to pay to use it. Of course, the charge for academics and industry is different, but in principle, everybody in India or even abroad has access to this. You can book it online and you can perform your measurements. So this is a Lakeshore cryogenic prober. It goes to liquid helium temperature. It's a closed circuit system. So once you fill in the liquid helium, which has become very expensive after the COVID pandemic, it was expensive, it is now even more expensive. So once you fill in the liquid helium, it lasts for 4 or 5 years before you have to do a refill, right. It has a sample stage which I will show, which goes to 4 Kelvin, 4.2 Kelvin, and the probes will be maintained at 15 Kelvin. Okay. There is a superconducting magnet here. This is a 7.5 Tesla magnet. Yeah. So for some of the cryogenic operations of, so a lot of people who are doing spintronics work and so on, right, they also use this kind of prober, and they need very high magnetic fields. So people are even asking for 12 Tesla these days. Okay, but for quantum computing work, even 2.5 Tesla will be enough. But that also is fairly high field. You will not get it without a superconducting magnet. All kind of ring magnets and so on, they come with the system. They will not be able to give you that field. So that's the electronics rack for this prober. This is our measurement system, Keysight B1500, switch matrix. Of course, nothing happens without a computer these days. This is inside view of this chamber. This chamber stays in ultra high vacuum. This will be maintained at -6 torr kind of vacuum. You see the probes here, and there is a lot of science that has gone in here in order to isolate all this outside world thermal load from affecting this temperature of this substrate stage. So this is a small substrate stage of around 2-inch diameter. Okay, so this is how it looks like on a these probes look like on a actual device. But as I said, we have just 4 probes. So, and these are non-Kelvin tungsten probes, right? So it's not possible to use this kind of a setup to measure actual qubit or even working SET for that matter. So our package-based setup we have custom created. We customized this probe station, And now what we have is we have a what is called as a QDAC, is a company Quantum Devil selling this DAC. This has 24 channels, and then there is a breakout box connected to the DAC. So 24 lines are traveling from here through a Fisher cable into this chamber. Okay, so those 24 lines reach through the Fisher cable into this chamber, and you have the supply for this DAC. So this DAC can give you DC, ground, and some kind of AWG function also on each of those 24 channels parallelly, independently. So now you can measure a device which requires up to 24 contacts. But your device is like this, right? This is what typically foundry gives you. Your collaborator will give you a wafer like this. I mean, these contact pads that are visible, these are barely like 40 by 40 micron in size, which is what is industry standard right now in CMOS. So how do you connect these pads to outside world? That's a big challenge we are facing, right? Some part I have not shown here, but there is this is some NDA, so we could not show it. But there's basically a PCB here, which is what we call as a sample PCB. It has a chip mounted, which has devices like qubits and single electron transistors and so on. Then so this has 48 connections to the chip. Chip is wire bonded to this PCB. Those 48 connections travel through this connector to a larger PCB, which is something we call as adapter PCB, and then this PCB through a wire loom, it connects to the Fisher cable here. So this is a standard MDM connector, right? So this has 24 2 MDM connectors that you can plug into this Fisher cable. So that's how the signal is reaching from outside world to this PCB. So of course you have to have thermal bobbins and all kind of this cryo technology to even cool down the electrical signal. So electrons which are coming from here are coming at a higher temperature, right? So if you don't cool the electrons, all your measurements are destroyed. So you have sort of thermal anchors which are tied to this stage somewhere. So electrons first go there, get cooled off, and then go into your device, right? So that they don't heat it up. So fascinating work, a lot of new characterization challenges. This block diagram of this system, I have already explained what it does. So now at present we do not have this kind of a dilution refrigerator, so all we have is the cryo prober. So many advantages are there. So every time you are contacting the chip with these probes, and then you change the temperature. Let's say you did measurement at 4 Kelvin, now you want to do measurement at 10 Kelvin. This is tungsten, this top metal may be aluminum. They have different thermal expansion coefficients. So in 6 degree Kelvin change of temperature, this will elongate differently, so it will actually end up scratching your pad. So you have to lift up the probe when you change temperature. Then you put it down, but contact resistance may have changed, right? You do it at 10 temperatures, you have 10 different contact resistances included in your analysis. So not a good idea. That's why this kind of a system is much better. Everything is connected, one shot, no use of probes. So that's a definite advantage. So you can measure a single device many times, otherwise these probes 4 or 5 times you put them down, they peel off the top metal and end up getting high contact resistance. So simultaneously you can operate more control lines. So using something like 48 control lines, if you are looking at charge-based qubits, you can at least hope to measure 4 to 6 qubits at the same time. So challenges, of course, number of devices again is limited by whatever context you have, right? Which is also going to be the problem, as I said, why cryo controller chip is required, that multiplexing, because it is always going to be limited. If you're talking about 100 qubits, there's no way you can do this, right? You need that multiplexer. Of course, wire bonding, we are facing a lot of problem. In the US, it's not being done. In Europe, it's not being done. There's only one company in Shanghai which is actually doing it. Couple of companies I talked to in Bangalore, in NCR, they said initially they'll do it, but they could not. Okay. So wire bonding is a problem. We are now in IIT Delhi Nano Research Facility. We have a wire bonder. Students are burning their midnight oil trying to do this, but they are actually successful. At a research level, they are able to do it. It's not a perfect job done, but jugaad is there. It's workable solution, right? That's what we call a jugaad. Of course, you have to use packaging materials so that you do not have too much self-heating effect. Heat can escape. So you are not talking about epoxies and resins, right? So this actually in a way brings us device guys much closer to a system level approach, right? Where you're talking about how to fix things and how to contact things. So that's one thing I like about this area. So as I said, we looked at the BSIM CMG model. These are room temperature correlation plots. So at room temperature with our devices, again IBM devices, everything looks kind of acceptable, right? Not perfect, but you can always decenter it and make a better aspect model and do it, right? So this is an acceptable model hardware correlation. We have published it in solid state electronics also last year. But when you go to the cryogenic temperatures, you can see that your subthreshold swing is not being modeled correctly by the stock model. So then basically what you try to do, and also you have to think about this kind of data points. How reliable is your data? How many times you can do these measurements? So basically you then augment the model with sort of better equations. This is all Verilog based, so very student friendly in that sense to optimize. They try to find out a critical temperature below which the equation switches from something like this to this. Similar things they have done for mobility modeling. All this is there in that solid state electronics paper if you are interested, or in EDL also we have published this year, early this year. So you can look at these, how this model is extracted and so on. So in interest of time, I am going to skip a couple of slides. We have looked at TDDB, for instance. This is dielectric background at cryo temperatures. We got reasonable results. We expect TDDB to be better at cryogenic temperatures, which is what turns out to be, right? So T63, if you look at, is much higher at cryogenic temperatures. So dielectrics are well behaved. A couple of things we noticed in the TDDB model that we have tried to highlight in IRPS this year. So there's a lot of discussion on this kind of shape parameter and so on. So in summary, we have looked at BSIM CMG correlation. We have tried to augment BSIM CMG so that it is possible to design circuits that can work at cryo temperatures. The accuracy is visible through the model hardware correlation results, and TDDB we have looked at for cryogenic temperatures, and we got expected results, and we have been able to explain those results. Of course, this is just the tip of the iceberg. We have just started working on this area in last 2 years. For a good 5 to 10 years time frame, we'll uncover a lot of new issues, new challenges, and probably reach new frontiers of success in this area. So with that, I'll thank you all for your attention. Any questions, I'll be happy to answer.
Thank you so much, Professor Dixit, for this wonderful talk. So questions from the audience? Yeah, please.
Thank you, Professor, for the wonderful talk. So as you have found DC probe,
yes.
Can we use the RF probe?
Very good question. We actually, so if you look at this, we have 4 DC probes, 1, 2, 3, 4, right? But there are 6 ports. So there are 2 empty ports. We have RF probe arms from the same vendor. We have the RF probes. Unfortunately, this was the first RF cryo system in India. So the vendor, who is the vendor representative, actually representative of Lakeshore. Lakeshore is a Canadian company. So their India representative, they did not take good care while ordering this system. So they gave us wrong kinds of RF probes. So they have magnetic and non-magnetic probes. They gave us the wrong ones, which would not make contact. So as a result, we have not been able to do this, but we have another system in the care department in IIT Delhi. This system is also limited in the fact that it has a very high magnetic field superconducting magnet. So the thermal load of this magnet doesn't let this system go below 8 or 9 Kelvin. The other system in care department is without this magnet. It only has ring magnet, so that goes to actually 4 Kelvin. There we have installed the RF probes successfully. So yes, RF probes are there. and we have done successful measurements. We have done SOLT calibration. Of course, you have to work with cryogenic compatible everything. So cryogenic RF probes are more expensive even for room temperature systems. So cryogenic RF probes are even more expensive. You have to have cryogenic RF probe arms. You have to have cryogenic standard impedance substrate. The room temperature substrate also will not work. The only company that makes these RF probes for cryo systems is called a company called Pico Probes. Okay, and you have no other option but to use their standard impedance substrate, which also is very expensive. So it is there, it is working at a premium cost. Yes. Yeah.
Any other question from the audience?
Thank you, sir, for the wonderful talk. So one thing I would like to know from your perspective, that usually at low temperature the variability is much higher. So when we have when we are talking about like 10 milli-K and all, do you think that the variability will be another issue that we have to take care?
Good question, Professor Lagere. Whatever experience we have had with variability, you can typically divide it in two parts. One, we are talking about static variability, other you are talking about dynamic variability. Okay, you combine the two and talk about overall variability, look at the ACLVs and so on. But so static variability is coming from the fabrication of device, which is not going to change at cryogenic temperature, right? Things that are going to change is at the operating time, which is the dynamic variability. So there, at present, we do not have sufficient data to comment whether dynamic variability is better or worse. The reason is, this is a fairly slow measurement, right? To operate a cryogenic prober, you load your chip or your substrate on the system. You have to wait for 5 hours before it achieves the right temperature. 1 or 2 hours you do the measurements, then you have to wait another 3 hours before you can open the chamber and check it again. At one point of time you cannot measure multiple devices. So that kind of data for variability study, so far we have not been able to generate, but in the PDDB work that I have shown, where we are making these Weibull plots and so on, there the student has measured at least 10 devices, 10 identical devices. So if she has not put in the gate current plot here, but there you would see that variability is not worse than what you see at room temperature. So I can't make a definite statement on whether it is better or worse. Maybe with more data in future we'll be able to address that.
On this actual temperature, how do we know what exactly is the actual temperature?
Yeah, that's the holy grail currently. So I talked to the vendors of this prober. They can give you a stick-on thermal sensor. So stick-on thermal sensor is something that you can, I don't know, where is that slide gone? Just give me a second. So in a system like this, you put your chip here, you can stick your sensor here using a epoxy and measure the temperature on the surface of your wafer. That as far as you can go with the vendor. If you really want to know what is the junction temperature, then you have no other option but to again fall back to that self-heating kind of analysis, heater and sensor and all that. Those kind of devices we now have, we just got from one of the vendors, where they have all this heater, sensor, gate resistance, all kind of layout, but we have not been able to put it to measurement yet. But we'll do that. We'll do that. Maybe within next 2 to 3 months we'll have done that. Yeah. Okay.
Any other question? So Professor Dikshit, I have one query. I mean,
yes.
So that PCB that you were showing, so that's kind of doing the role of analog switch matrix, right?
Yes.
Using like,
it's a multiplexer.
Yeah. So can we use the switch matrix that is provided by these parameter analyzers and then like probe it?
No. So you can, but this is what I said, right? this is how people actually started doing it. But the problem is, this is a sort of adiabatic enclosures, right? So now instead of routing those two cables, so our Fisher connector comes till here. Fisher connector is hermetically sealed.
Oh.
Okay. So it is not going to take away, basically put in any extra thermal load in here to this point. But if you want to do that switching rather than from here to here, so instead of those two cables going from here to here, you will have 48 cables going all the way up here, right? So thermal load will immensely increase. So that's the reason you need that adapter and sample PCB. But once you have a cryo controller,
Yes.
this is the kind of interface where you will mount it, and then you can operate many qubits.
And one more query, like we were looking at these anomalous trends in the subthreshold swing and the threshold voltage at cryo temperatures. So many people have explained it using very high interface states, 10 power 14 per centimeter square, 10 power 13 per centimeter square. I mean, those values, do you observe them really in the modern transistors, or they are just for modeling purposes that they've used it?
No, there is substance to it. Just a couple of days ago, I was reviewing work of one of my students who is working on low frequency noise.
Sure.
So she actually measured low frequency noise in cryogenic temperature, and she back calculated the trap density.
Okay.
So trap density is actually NOT, the oxide trap density is coming out to be 10 to the 13, 14,
Yeah, exactly.
right? Which is something you set at 10 to the 10 at the time of manufacturing.
Yes.
So lot more traps are getting activated and participating in capture, decapture, right, at cryogenic temperature. So this is a new thing we have just now observed. So somebody actually pointed out how can the traps be so high.
Yes, exactly.
So, but experimentally we are even back calculating and we are getting trap densities of that order.
Maybe this back calculation thing, maybe the procedure is not, like
Possible.
may not be
See,
correct.
this is advanced research, right?
Yes,
you have
yes.
to look at all kinds of options, and you have to sort of
At what temperature is the lifetime getting longer, the captured lifetime, and so they are contributing to the capture contributing?
so yes. So lifetimes we have measured, at least the TDDB lifetimes we have measured. So they are much longer. I have shown that data. They are much longer at cryogenic temperatures. So actually, if you read our TDDB paper, this one that is just published in IRPS, we have explained based on the trap numbers and trap size, we have explained the phenomena that we observed in TDDB. So you can see that TDDB lifetime, this is 300 Kelvin, this is 10 Kelvin or low. You can see that it is actually gone out at least 2 orders or even more, 3 orders it is higher, right? So traps have a very effective role to play. So people are not wrong in giving those high number of traps. There's a lot of trap activation happening at cryogenic temperatures. We have to find out the physics and material science behind what is actually happening. Yeah.
So as a token of gratitude, we have some gift for Professor.
Oh.
I request Professor Chauhan to give it to you.
Yeah. Thank you. Shake hands.
Thank you so much, Professor Dixit. So now we